Check this out. At the Colosseum in Rome, an underground passageway that was used long ago by high-ranking officials is now open to the public.
When researchers asked Grok AI to digitally rebuild the Colosseum, they expected history, not mystery. But what the AI found inside the ancient stone left scientists speechless. Hidden tunnels no one had mapped, patterns in the walls that defied symmetry, and secrets suggesting the Romans may have known more about engineering and the Earth itself than we ever imagined. The Colosseum wasn't just built to last, it was built to think. Let's go. When Grok AI reconstructed the Colosseum, when researchers fed Grok AI the data, they expected a routine reconstruction. What they got instead left them speechless. The digital model began to reveal something that no human eye had ever seen: hidden alignments, unexplained voids, and patterns that didn't belong in a structure built nearly 2,000 years ago. The Colosseum, the most studied monument on Earth, suddenly appeared to contain secrets that had gone unnoticed for centuries. Could artificial intelligence have just uncovered an ancient code buried in stone? Did the Romans design something far more advanced than we ever imagined? And if so, what was its purpose? Grok AI was a next-generation neural network designed to interpret incomplete or fragmented data, a kind of digital archaeologist that could see beyond the missing pieces. Engineers developed it to simulate ancient environments by merging satellite imagery, laser scans, historical maps, and even micro-vibrations measured from the ground. When the Italian Heritage Board announced that its 2025 integrated digital survey of the Colosseum was complete, Grok became the obvious candidate to make sense of the enormous data set. The data was staggering in scale: more than 108 billion laser-scanned points, 208,000 high-resolution drone photographs, and terabytes of measurements detailing everything from stone composition to the humidity levels within the underground corridors. Every inch of the Colosseum had been digitized, from the upper spectator terraces down to the lowest service tunnels. The goal was to create the first true digital twin of the monument, a three-dimensional model so detailed that it could simulate how the amphitheater once looked, sounded, and even moved. Researchers expected a faithful visual replica. What they didn't expect was for Grok to behave like a detective. Instead of simply stitching the scans together, it began identifying patterns, micro-deviations in structure that human analysts had previously dismissed as natural wear or construction error. As the model refined itself, the AI flagged hundreds of tiny asymmetries. Walls that should have been parallel were off by a few millimeters. Columns that looked perfectly aligned to the naked eye were tilted at subtle but consistent angles. At first, the team assumed it was noise in the data, but the more Grok analyzed, the more coherent the irregularities became. They weren't random. They repeated in a circular rhythm, like a fingerprint embedded in stone. The AI's geometric mapping revealed that these offsets formed a sequence, a mathematical pattern that rippled outward from the Colosseum's center, almost like concentric sound waves. When the AI simulated physical stresses such as wind pressure, crowd weight, or seismic vibration, the reason became clearer. The misalignments distributed stress more evenly across the entire structure, preventing resonance that could cause cracks or collapse. In simple terms, it appeared that the Romans had built an earthquake-resistant amphitheater, and done so deliberately. Grok calculated that the pattern reduced vertical strain by nearly 8% under simulated seismic loads, an engineering principle that modern architects only rediscovered in the 20th century. Even more remarkably, the pattern's geometry corresponded with optimal acoustic diffusion, allowing sound to travel evenly across the seating area. The same features that stabilized the building also amplified the roar of the crowd. One researcher described it as ancient active design, centuries before the language to describe it existed. The finding was so unusual that Grok's own developers double-checked for machine bias, wondering if the neural network had invented correlations where none existed. But the numbers held up, every small deviation repeated with near mathematical precision. If these were mistakes, they were astonishingly consistent mistakes, Then came the deeper shock. When Grok attempted to fill in missing data from the lower levels, the sections where ground-penetrating scans were incomplete, it began reconstructing features that didn't appear in any archaeological record. Using probabilistic modeling, the AI predicted the presence of several sealed tunnels beneath the hypogeum, the subterranean area where animals and gladiators once waited before battle. These tunnels connected to what appeared to be a narrow corridor running diagonally toward the south side, almost perfectly aligned with the recently opened Passaggio di Comodo, the imperial tunnel believed to have been used by emperors to move unseen through the arena.
Corridor that was built inside the foundation, so something very interesting.
But Grok's model extended the corridor much farther than the known passage. According to its simulation, the tunnel continued beneath the modern surface into an unexcavated zone that current maps showed as solid ground. At the end of this line, the AI indicated a circular void roughly 8 meters wide and 3 meters deep, sitting directly under the geometric center of the arena. When projected into 3 dimensions, the void resembled a hydraulic chamber, a kind of reservoir or base for a lifting mechanism. The resemblance to ancient Roman hydraulic systems was uncanny. Archaeologists have long known that the Colosseum once featured elaborate lifts powered by pulleys and water pressure, used to raise animals or stage props to the surface. But no physical evidence of a central hydraulic base has ever been found. Grok's reconstruction suggested that such a system might still be buried intact, sealed off after the arena's decline. Its position beneath the central axis matched the engineering logic of a main counterweight or water reservoir that could have balanced smaller side lifts. When the research team published its preliminary findings, the academic world reacted cautiously. Historians argued that the AI's output was an example of overfitting, finding meaning where there was none. They pointed out that centuries of earthquakes, fires, and restorations could easily explain the slight asymmetries and voids. But others weren't so sure. Structural engineers who reviewed Grok's data noticed something unsettling. The same off-center geometry appeared to follow modern principles of seismic damping. It was as if the builders had instinctively designed the Colosseum to flex and absorb shocks, exactly the way 21st century architects reinforce skyscrapers today. Physicists ran independent simulations and confirmed that the pattern Grok identified would indeed reduce harmonic resonance, the dangerous oscillations that cause structures to fail during earthquakes. The AI's discovery wasn't proof of lost technology, but it did imply a level of empirical understanding that the Romans should not, by conventional wisdom, have possessed. Grok AI had exposed a logic hidden within the ruins. To understand why this discovery matters and how it could even be possible, we need to go back 2,000 years to the people who built it. The secrets of Roman engineering, genius behind the stone. The most recent findings shocked even the experts, who thought nothing new could ever be learned about the Colosseum. In early 2025, researchers at the Sapienza University of Rome announced that the monument's ancient concrete had not only survived 2 millennia, it was still chemically active. The material appeared to heal itself when exposed to water, resealing micro-cracks that would have destroyed modern concrete within decades. It wasn't science fiction, it was Roman engineering. The same self-repairing chemistry that we only recently learned to replicate in laboratories had been working silently beneath Rome's streets for almost 2,000 years. Could this be why Grok's reconstruction revealed such perfect resilience? Could the AI have uncovered not coincidence, but the physical proof of forgotten science? To understand how Grok's simulated revelations could even make sense, we have to go back to the origins of the Colosseum itself, to the years between 72 and 80 AD, when Emperor Vespasian and his son Titus began a project so immense it redefined what human civilization thought possible. Imagine coordinating tens of thousands of laborers, quarrying millions of tons of travertine stone, and transporting them through crowded streets using ox-drawn carts and wooden cranes powered by hand. The sheer logistical scale of this operation bordered on impossible, And yet, the Romans made it routine. Within less than a decade, they built an arena capable of holding 50,000 people, an amphitheater larger than most modern stadiums, and astonishingly, constructed without modern machinery. The secret lay in how they mastered space. The Colosseum's vault system, a complex web of arches and corridors, distributed weight so evenly that the structure could rise higher and cover a larger area than anything before it. These vaults weren't random. They formed an interlocking grid of radial and concentric arches that absorbed pressure from every direction. By stacking these arches in layered rings, Roman engineers created a self-supporting skeleton of stone and concrete that could withstand centuries of earthquakes, fires, and even medieval scavenging. Modern simulations now show that its stress distribution is nearly identical to 21st century stadium designs, but it was their use of concrete that truly changed history. Roman builders mixed volcanic ash, known as pozzolana, with lime and seawater to create a chemical reaction that formed compounds capable of binding underwater and resisting decay. Modern scientists have discovered that within this mixture were tiny lime clasts, unreacted fragments of calcium oxide, that when water seeped in over centuries, reactivated and filled cracks from the inside. It's why sections of the Colosseum and Roman harbors still stand strong after nearly 2,000 years. When Grok analyzed the material data, it confirmed something extraordinary. The microscopic structure of Roman concrete resembled a living system, constantly adapting to its environment. And yet, what happened above the surface was only half the story. Beneath the Colosseum lay an entire world that once moved with astonishing precision. Archaeologists call it the hypogeum, a vast two-level maze of corridors, ramps, pulleys, and cages that brought animals and stage scenery into the arena through hidden trapdoors. For centuries, it was thought to be little more than a storage area. But new excavations between 2022 and 2023 changed everything. Researchers uncovered hydraulic channels, wooden grooves etched by centuries of moving machinery, and traces of ancient oils used to lubricate gears. They even found the remains of food discarded by workers: olives, barley, figs, frozen in time beneath the arena floor. What these discoveries revealed was a machine disguised as a building. The Colosseum's underground system relied on a network of pulleys and counterweights, powered by both human labor and hydraulic pressure. Using water drawn from nearby aqueducts, Roman engineers could raise massive platforms silently and swiftly. Some historians once doubted ancient accounts describing whole herds of animals or full-scale trees appearing on stage in seconds. But the mechanical evidence now supports it. Each lift shard was connected to wooden hoists that could be reset and reused between shows, creating a cycle of motion and illusion unmatched in any ancient performance space.
Up through the ramp could come animals or people, appearing as if by magic in the arena.
But the Roman genius didn't stop at structure and mechanics. It extended into physics long before the concept existed. In early 2025, a collaborative study by seismic engineers from the Polytechnic University of Milan and the University of Naples revealed that the Colosseum behaves almost like a tuned instrument during earthquakes. Sensors placed throughout the structure detected that its arches flex and resonate in ways that disperse energy rather than absorb it. Instead of resisting vibration rigidly, the amphitheater bends, then rebounds, exactly how a modern building designed for earthquake resistance behaves. When this data was compared to Grok's geometric mapping, the overlap was remarkable. The same asymmetric alignments the AI had identified, those subtle deviations in wall placement and column angle, directly matched the zones where natural vibration energy was least intense. In other words, the very imperfections that Grok discovered were part of an intentional damping system. Roman engineers may have understood, through empirical observation, that symmetry was not always strength. By slightly breaking perfect balance, they allowed the structure to move without breaking. It was as if the Colosseum itself had been tuned to the rhythm of the Earth. Now, Grok's findings add another dimension to this mystery. The repeating geometric pattern hidden in the Colosseum's design, once thought to be an error, may correspond to solar alignments that marked significant religious or political events in the Roman calendar. When the AI reconstructed the monument's light simulations, it found that certain corridors and archways lined up precisely with the sunrise on the festival of Venus Genitrix, the goddess linked to the Julian family, ancestors of Emperor Augustus. If this alignment was intentional, the Colosseum may have served as more than an arena. It may have been a symbolic engine, channeling celestial and earthly power into one monumental space. So were these asymmetries purely structural genius, or something even more profound? AI versus archaeology, when data challenges history. After the success of the first model, Grok's engineers decided to test its reasoning further. They refined its dataset using what's called HBIM, Historic Building Information Modeling, which merges laser scans, historical archives, and restoration data into a single interactive environment. This was a level of precision never achieved before. Over 100 billion points of measurement, updated with the latest drone imagery and geological mapping from the Italian National Institute of Geophysics. When Grok processed this enormous dataset, it did something new. It stopped acting like a static simulator and started behaving like a predictive system. The second model showed how the Colosseum functioned, how it aged, and how it might have felt to stand inside it at its peak.
The Colosseum was, and still is, colossal. It's the great example of ancient Roman engineering.
It recreated the weight of a crowd, the resonance of footsteps, and the mechanical hum of its subterranean machinery. Within hours, the simulation had identified something that centuries of archaeology had missed. The Colosseum's center of gravity was not in the geometric middle of the structure. It was slightly displaced toward the northern side, a tiny but deliberate offset. The AI cross-referenced this with geological data and confirmed that the southern foundations sit on softer soil, historically prone to subsidence. In other words, the ancient builders had compensated for unstable ground by shifting the building's balance, preventing collapse through design alone. No human had ever measured this with such clarity, though the effects had long been visible: subtle tilts, uneven settling, minor cracks. But Grok's discovery reframed those as intentional corrections rather than construction flaws. The amphitheater, it seemed, wasn't just designed to stand tall. It was designed to endure the shifting earth itself. This insight alone was revolutionary. It implied that Roman engineers not only understood the material behavior of concrete and stone, but also the dynamic forces of soil and vibration beneath their feet. As the simulation evolved, Grok began generating hypotheses, visual and mathematical models that suggested why certain choices were made. It predicted that the asymmetric vaults acted as dampers, redistributing stress when tens of thousands of spectators stamped, or when tremors shook the city. It also modeled air and sound flow through the corridors, revealing a network that amplified certain frequencies while dampening others, allowing the emperor's voice to carry effortlessly while crowd noise dispersed. What looked chaotic in ruins became harmonious in motion. Then Grok went one step further. Using data from pigment residues and mineral analyses, it reconstructed what the Colosseum might have looked like when it first opened under Emperor Titus. The arena's outer walls, long stripped bare, were once painted in deep red and ochre. The statues that filled the arches gleamed with bronze and gold. Even the seats, Grok suggested, were color-coded to organize crowds by class and rank. The AI's final render showed a structure so alive with movement, sound, and color that it felt almost alien compared to the bleached stone we see today. It wasn't a ruin of history. It was the heartbeat of an empire. But what made this even more unsettling for scholars was the AI's interpretation of intention. Grok didn't simply reconstruct what existed, It tried to infer why it existed that way. Its pattern recognition algorithms identified relationships between structure, environment, and purpose that no human analysis had captured. For example, the offset geometry wasn't just structural. It mirrored the tilt of the sun during the summer solstice, as if the building had been aligned both with the Earth and the heavens. Grok's data-driven conclusion was that the Colosseum was designed to function as both a machine of spectacle and a symbol of cosmic order, an instrument that united engineering, astronomy, and theology. One historian at Cambridge called Grok's simulation a mirror held up to human imagination. He pointed out that the AI was reflecting our own desire to find meaning in complexity, just as ancient architects might have sought divine patterns in stone. Yet, this comparison raised a deeper question. If an AI could accurately model how ancient builders compensated for soil movement, predicted vibration, and manipulated sound, then it was essentially reverse engineering the thought processes of people who lived nearly 2,000 years ago. What happens when a machine begins to understand the minds of the ancients more clearly than we do? Does it become an archaeologist, or a kind of historian in its own right? But perhaps the most haunting part of Grok's achievement is what it revealed about us. Every time the AI refined its model, it needed less human input. The more data it absorbed, the more confidently it predicted the intentions behind ancient choices. It wasn't just filling gaps in broken ruins, it was building bridges between lost knowledge and modern logic. It began to see patterns in how civilizations think, how they evolve, and how they embed meaning into their creations. Maybe that's why this discovery feels so unsettling. When Grok simulated the Colosseum as a living organism, a structure that flexed, healed, and responded, it blurred the boundary between the human and the artificial, between history and prediction. The Colosseum became more than a relic.
When in Rome, go to the Colosseum. The ancient gladiator arena is a must-see attraction in the Eternal City, and starting next month.
It became a dialogue between two intelligences separated by 20 centuries, one carved in stone, the other written in code. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.